able to know the 5-number summary quickly and easily is always least to greatest. Laura, 1,000 points right there. And let's do this.
I found him. What's he doing? I don't know.
The 5-number summary is the following values.
He's talking to someone.
From least to greatest, min, Q1, median, Q3, and the max. Nice answers. If you put the 5-number summary in the chat, you get 1,000 points. Keep these answers coming.
What is it?
Hey everyone, how are we doing? People cracking up right there. Some Stranger Things going on. Brian teaching stats and stuck in the upside down right there. No spoilers on Stranger Things. But with this right here, Max asked such an amazing question about 0.05. And why do we have 0.05? Let's talk about that briefly here. Good to see you, Adam. Good to see you here, Kevin. Good to see you here, Dana. Good to see you here, David. Brilliant Cinematics. And that's thanks to Jason Greenway at the Haslam College of Business. One of my good friends right there, Jason. I need to see Jason. I miss seeing everybody. Oh, man, I miss seeing Jason. So Max was asking about that 0.05 p-value and what does a 0.05 p-value mean? Well, when we get a p-value, it's the probability of our results or results more extreme by the probability of our results or results more extreme happening by random chance variation given that the null hypothesis is true. So we also have to think about what is the null hypothesis. In a lot of instances, it might be something like, it's kind of a way we can talk about it, that the r squared is equal to 0. So, and then that will do an F statistics. Let's do correlation is equal to 0. Correlation is equal to 0. So if there is no correlation, what would be a likely thing to see? What would be, if there's no correlation, trying to find another way to talk about this. If there's no correlation, what would be a likely thing to see? If there is no correlation, what would be a likely thing to see? Given, like if you write out this as a null hypothesis, the null hypothesis here is that correlation, rather rho, I think rho is P. I always hate that. We'll just write core equals 0. If the correlation is equal to 0, then what's a likely thing to see? If the correlation is equal to 0, then a likely thing to see would be what? Help me out for 100 points. Help me out. If the correlation is equal to 0, then what would be a likely thing to see? If the correlation is 0, then a likely thing to see, well, and it would have a high p-value. You are right, David. Throw some points right there. The likely things will have high p-values, and a likely thing to see, which would have a high p-value, would be what? And I'm shading the region right now, would be correlations what? Which would be like, if correlation is 0, assuming correlation is 0, then a likely thing to see when we run a correlation test or when we get a correlation would be a correlation close to what? A likely thing to see. A likely thing to see if correlation is 0. Correlation is close to 0, Max earning everyone another 100 points. Correlation is close to 0 would be very likely by random chance if there is no correlation. And which would be a straight line too. Yes, that is correct. Great job, Mon, right there. It would turn into a straight line where X and Y would have sort of because correlation can measure the linear strength. So we're more likely to see things like this, which would land somewhere here. Now, we're not always going to land right on there. We might land here. Was the correlation, it might go a little bit down, was the correlation for this line that I just drew equal to 0? Yes or no? Was the correlation exactly 0? For this line, which goes a little bit down, is it exactly 0? Is the correlation exactly 0? Is the correlation like exactly 0? If I were to write the value of correlation for this, and I write R equals, no, it's going to be negative because the line goes a tiny bit down. It's going to be like negative 0.04. So what would be a correlation just as extreme as negative 0.04? A correlation just as extreme as negative 0.04 would be what? We're not truthfully solving out the pure mathematics. We're talking theory right now, so don't worry about how we found the 0.04. We're just saying if that has a correlation of 0.04, what would be a correlation just as extreme as 0.04? Positive 0.04. And now, since we know our results, and we know a result just as extreme, and then we know what is likely by random chance, we could go right here and shade the what? Knowing the outside portions of this will get us the what, which looks very large, telling us that this result or a result more extreme would occur by random chance, maybe like 80% of the time. This is a very large p-value. That's the shaded p-value. So Max was asking, like, if the p-value here is something like 80%, like the p-value here is equal to 80%, well, then what's the complement of the p-value? The complement of the p-value is going to be the inner region right here, which is results less extreme than ours by random chance. We don't often usually concern ourselves with that, but it's such a good question. Like, well, then what is the other side of it? Well, results less extreme than our result would occur by this by random chance. So we're usually concerned if our result is unlikely by random chance, and then you could say the results that were more likely than ours would be the 20%. So the inner portion of that, the other side of it would be the 20%. Does that make sense, Max? It's a really good theoretical question. And then understanding how these p-values are calculated and what we're doing. If we were to do it with an R-squared, it would be a little bit different. The graph would look more like, and I'll show you. It's going to look like, I think this will plot it if I do possible regression on this. That's plotting it right here. So this right here is my regression model. Maybe I'll make it a little bit smaller. And this is doing the same test right here with a reduction of sums of squares. So if you notice right here, here is my regression model. Now, if you notice, what is the big issue with this regression model? You should immediately see this. This is a great review. We're going to hop into some new notes here in a second. But you should immediately see a problem with the regression model. What problem do you see instantaneous with that regression model? Instantaneously, I see a problem. You should see a problem with that regression model. So you should say it's not linear. Great job right there, Daniel. Excellent work. Throwing some more points out. Is not linear, not straight enough. So remember, our conditions are that we have linearity, equal spread of residuals, and normality of residuals. We're not really doing a check regression on it, but we're just looking at that, and it obviously violates a linear condition. It's actually a pretty decent model. It has an R-squared of 97%, but it's horribly wrong on one of the conditions. All models are wrong. Some are useful. But if you were to do the test over here, the p-value is 0. Why? What is the smallest reduction in sums of squared error possible? What is the smallest reduction in sums of squared error possible? The answer is on the screen. The smallest possible reduction in the sums of squared error possible is what reduction? I mean, just think you're trying to reduce the error, so what's the smallest reduction you could get? The smallest reduction in the sums of squared error is what? The smallest reduction possible, I'll have to disappear so we can talk about this, is what? Scientific notation right here, so it's a little bit confusing, but it's just 0 Veda. Great job right there, Veda. Alyssa, good to see you here. It's 0. So what are we seeing right here? These are the reductions by what? They're from the permutation procedure, so these are the reductions created by what? From the permutation procedure. So even though the model gets you 97% of the way... so here, Max, I'll explain on that in a second. Max, another great question. So, and no, it's such a good... This came from the 474 class today, which you'll notice there's a lot of... got a huge compliment from a student. They said, I really love how every class leads into it. They're like, what I learn in 320 is used in 474, which is used in 475, which is used in 471, which is used in 479. Like every class shares components of what we teach. There's a lot of succinctness to what you learned throughout business analytics. So whatever you're learning here, if you get it down, you know it for other classes. So all of these right here are created what? Does anyone remember the procedure we do to create these? These are all random whats. Random whats are being created right here, which is looking at what we would see by random chance. So it's just random permutations. These are random permutations where we mix up the x and the y, and thus the reductions in sums of squared error would be very what by random chance. By random chance, reductions in sums of squared error are usually very what? Just look at where they're at. Look at the side they're at. Reductions of sums of squared error by random chance would be expected to be, sometimes they're a little bit larger, but they'd be expected to be very what? Reductions of sums of squared error by random chance. When we just mix up exactly mun, great answers right there. The reductions of sums of squared error by random chance is expected to be very small. Our observed reduction is way over here, which there is no random chance observation that is as extreme as ours or more extreme. So the p-value is estimated to be 0, telling us the reduction we observe is basically impossible by random chance. And this is a very advanced way of doing p-values. You oftentimes see a p-value down here done via statistical test with degrees of freedom. So this is the overall test of the model, which we've talked a lot about. And then Max asked another great... Max, you're just crushing it on this question. Then more points, Max, right there. So even though this model gets us 97% of the way to understanding why, and great way of explaining it right there, what are our thoughts on it? Well, this model is definitely what? One word. This model is definitely wrong. But look at how good this model is. It gets you 97% of the way to understanding why. So although this model is wrong, and you bet it's going to violate a linearity, and truthfully, it might not be able to run the linearity because we don't have repeat values. Yep, can't, but you... Which graphic do you look at for linearity? 1, 2, 3. 1, 2, 3. Which graphic we should know instantaneously? Which graphic do you look at for linearity? 1, 2, 3. A lot of people get this confused, but if you have it down, you know which one. It's 1. And look at this. There's that parabolic thing that we fit. This is the normality of residuals, which does have a problem too. The only thing that works is the equal spread. The equal spread is not violated because it's pretty constant, good equal spread. But even though this model looks ridiculous, this model gets you 97% of the way. There's the multiple. We want that one, actually. The model gets you 97% of the way. So please tell me, this model, while horrifically wrong, is probably a little bit what this. This model is very wrong, but might actually be a little bit this. This model is horrifically wrong, and I'll show you the notes that we were covering it from today. So you can see some notes from other classes. This model is horrifically wrong, but it might actually be what? I had them guess the R squared. A lot of people were guessing 70%, 80%. And I was like, that's in the upper 90s. This model is horrifically wrong, but is probably useful. I mean, it gets you decent. It gets you an idea. It's going to help, right? The parabolic model would be better, but this model right here is very super wrong, but might have some use. It's got a good R squared. 97% of the way is nothing to throw away. But we would acknowledge the problems, and in truth, you could just fit the parabolic. You could fit the polynomial model through this. So that's a really great review. Max, thank you so much. Max, 100 points. Keep those questions coming. Dare to be curious. Keep asking those questions. For the linearity plot, you want it to follow the line in the middle. Exactly. Cole, another 50 points. Cole, great answers too. Cole right there. For the linearity plot, this one right here, you want it to be going around that. Does that make sense? Like it doesn't really follow it. The points are just like around it. You see how it's like above it, below it, above it? That's the bad thing. If we did a random one, like if I do an X, random normal, these are just 100 random points. This should pass the linearity probably. Here, wait. No, let me do some. Let's do sample 1 through 10 and sample 100 observations with replace equals true. So this is just going to be X and Y are going to be, and then let's go to, they're just random. They're just random. And so now let's visualize it. And so we should see something that passes here. And what we want to see, and this is what you would expect. Wow. This looks a lot like the what model. And it looks to actually pass all the conditions. So now we have a model. Let's look at our conditions. Now we have a model that passes all the conditions. Normality didn't pass. Normality didn't pass. It passes all but normality. The equal spread is, are these points equally spread across this? And then the linearity is, does the line cut through the center of this? Like in the previous one, remember the line is not cutting through the center. Like this is not the center of these points. The line does not cut through the center. So now Mun is very correct. It looks like the naive model, and that means R squared is going to be super close to what? Like if you had to estimate the R squared of this model, what would you estimate the R squared of this model to be? This model does better on the conditions, but estimate the R squared. This model does way better on the conditions, but estimate the R squared of this model. It's super close to naive, and yeah, look at that. That's decimal notation right there for 0.12345, 5648. It explains fractions of it. Amazing work, great review. The R squared is basically 0 because the line is basically flat. And look at the R squared adjusted. What should we always remember about R squared adjusted? It can do this. What can R squared adjusted do that some people just say, what? That's impossible. R squared can't be this. Well, that's R squared adjusted, which is adjusted for how many variables are in the model. So it's always penalized. Even if there's one variable, it's still penalized. We usually think of it as a multiple world thing because that's when we have more X's, so there's more penalty. And it can be negative. So there's a good thing to see right there that R squared adjusted is negative, and that's like, haha, this is a horrible model. And so it's because I created random chance. Now, you don't always get ones by random chance that are bad. You could get random chance models. We'll take away the check regression. You could get a random chance model that actually has statistical significance. And this is where how do you interpret the R squared adjusted? Just say my model's super bad. R square adjusted does not have any real interpretation. It's a metric of our, you might say the penalized value of our R squared is 0.03736. Right now, this explains 4.7808% of the variation in Y, the X variable does. And this model is statistically significant with a p-value of 0.03, telling us that we think that the relationship is unlikely by random chance. But here's the thing. Is this relationship here by random chance? Yes or no? You might say, how would I know? Well, the code tells you the answer. Is this relationship right here by random chance? We know 100% certain whether or not it is right now for this one. Because the answer is on line 18 and 19. This is 100% by random chance. You can get p-values below 0.03. What's the probability of getting a p-value this low? 3%. That's what p-values are. It's telling you how unlikely this would be by random chance. So this was like a 1 in 33 chance of getting something this extreme, and we got something this extreme. It just happens 1 out of 33 times. Now, we actually got an even lower one. Now we got one that only occurs about 1 in 55 or 56 times. Now we get higher p-values. Oh, then we just got a super high p-value. The p-values are just completely random. If you were to graph the p-values right here, you'd probably see a uniform distribution because you're just going to get random p-values right now. Sometimes you'll get a low one, sometimes you'll get a high one, but the relationships right now are via random chance. You're not, if you see anything, it is by random chance. But if we take real data right here, we're going to hop to lecture after this, and we do something like the relationship between height and weight, and this goes back to Max's question. I want you to tell me about this p-value right here. How small is this p-value right here? Who knows what that is? That p-value, and I might actually be able to show it a little bit better. I love it. This p-value right here is this. That's the p-value. How small is this p-value? Wilton's right there. It's basically 0. Ridiculously small. So what is that telling you? The relationship between height and weight that we see here is basically what by random chance. Not that it's very unlikely, that the relationship we see now between height and weight right here is basically what by random chance. Like this relationship that we see between height and weight is virtually what by random chance. Virtually what that this would happen by random chance. Like, and then this is the way to think about p-values. And this is why you want super small p-values, because I'm saying what I'm seeing right here by random chance would be virtually this. Virtually impossible to occur by random chance. I totally believe, I am utterly convinced that there is a relationship where someone's height is explained by someone's weight to a certain degree. It doesn't mean I know someone's height if I know their weight, but there's a relationship to some degree. Like I would believe that they are associated in some way, that knowing someone's weight would give you information about someone's height. So that's what we're trying to do here. That's what we're trying to understand, is that p-values are not just that whole 0.05 thing. 0.05 is just something statisticians came up with to say, that's a good point to say it's statistically significant. What do we want? We don't want 0.05. If we're going to reject the null and say that there's evidence, basically not, but not. I don't know. We want super crazy small p-values. And this has been a good review, understanding p-values, understanding statistical significance, and when we want p-values to be super ridiculously small. Now, please note, and I want to put this last caveat, and please remember this because test is coming up next Wednesday. Are these good or bad right here? Are these good or bad? Do we like this? Yes or no? This is where you should, if you're seeing a check regression right here, do you like this? Yes or no? These are bad. This means we have violations of the conditions. Nathan, great job right there. This means we have violations of the conditions. And does this mean we have a little bit of evidence that we violated them or a lot of evidence that we violated them? Is this a little bit of evidence? Because it's saying the p-value is 0. Remember how the p-values are basically 0 over here? Is this a little bit of evidence of violating the conditions or a lot of evidence of violating the condition? It's a lot of evidence. The smaller the p-value, the more evidence you have for whatever you're looking for. And we don't want to find stuff here. P-value low doesn't always mean good. It means evidence of something. Previously, it meant evidence of a relationship between X and Y. So this low p-value on the screen right here is evidence of a relationship between X and Y. Meanwhile, this p-value right here is evidence of a problem with the linearity. Remember, with assumptions, we assume they're good till we have evidence they're bad. I would say we have some normality issue, we have some linearity, and I don't really see the equal spread, which is the highest, but still a very low p-value. Remember your scientific notation. That p-value is going to be this right here. Really? That's the same number? You're weird, R. I think it's because of my digits thing. Let me fix the digits. That was the weirdest thing ever. Oh, R is weird. We assume numerali, so a low p-value means we reject the null. Exactly, David. 50 points right there. David, exactly right. Low p-value here is evidence that the null hypothesis is wrong. Evidence against the null. Evidence for the alternative. Evidence the null is wrong. Here the null hypothesis is that we are good, so the p-value low is bad. Daniel and David crushing in another 50 points right there. Okay, we're hopping back to the main screen. But great job, everybody. Really good review. I want to make sure everyone's prepped for the test. We've got a good bit of time till the next assignment. Let's hop in here and let's take a look at some more notes. We're back in full swing. Man, I tell you, we're not talking about last week. We don't talk about last week. Last week is Fight Club. We don't talk about Fight Club. But it is good to be back and in full swing. We get to do so much fun stuff right here. I love these. 201 has some material that I don't love. Not that I like hate any of the material, but there's some chapters where I'm like, I don't like this chapter. But our class is organized in such a way that every chapter I absolutely love. I think it's because it's more... Stat 201 is more of a general purpose course where you learn things that are like, you know, things that all majors need to know. So we have to like do a potpourri of what you need to learn. But this is business analytics, so we get to do all the fun stuff. So let's hop here and start doing some fun stuff. Here we go. I'm going to get caught up on labeling all the videos this weekend. Sorry for the delays on labeling. Just got way behind last week. We don't talk about last week. P-values. Cole, 100 points. Cole, glad to hear that. And that's why we do some review. We got to review these things. We got to practice. And I promised you this. Oh, I do love coding. I absolutely love it. Shout outs to Business Analytics Society. Last night, the Business Analytics Society had their first meeting. And really, thanks you to, why can't I think of his name? Why can't I think of his name? Running the meeting. Talk to him all the time. Charlie Quick was there. Julie Ferrero was there. And Dennis. Oh, man. Thank you, everyone. Dennis right there. Dennis, RA on campus, doing an amazing job. Dennis really did so much work together. And Ahood, too. If you met Ahood at the meeting, Ahood made the flyer. So I'm hoping she's... that's her news to talk about. That's a lot of great news for everybody lately. Like, what do people want me to share or not share? So I don't know. But I'm honored by my students. Dennis... really, you know, so many people were asking about the Business Analytics Society, and Dennis was like, I got this. And he's done so much work to get things going. So big shout outs. And we're going to try to get Dan Richfield. I'm going to reach out to Dan Richfield, who can come and talk about programming, easy CGI, starting his own furniture repurposing company, or they took StormNet. That's cool. We'll bring Dan Richfield in. He said he wanted to do it, so he's on the line for it. But let's talk about those outliers. You know, Dan Richfield, let me just talk. I want to talk about Dan Richfield for a half second here. My friend Daniel Richfield is an outlier. Dan Richfield is an outlier because I want you to see something about him, which I'm very proud of him for doing. Go to the main screen here. Why is Dan Richfield an outlier? He retired in his 30s, took a break, and I want you to look at something. When did he go to college? When did he go to college? And he's like my mom. He went to community college. When did he go to college? When did he go to college? He went to college in 1999. Gosh, that makes people sound old these days, right? When do you think he graduated high school? So when would someone who went to college in 1999 graduate high school? Right for the dot-com bubble, right? So if he went to college in 1999, he'd be like a 1999 or 1998 high school graduate, right? When did he co-own a company for 10 years? When did he... Exactly. This is what I want to point out. Oh, no, he didn't graduate in 1995. I think he graduated in 98 or maybe 99. He might have graduated he's 98 or 99 high school graduate. And then he co-founded or co-owned his company right here. He was co-president, I believe, of a company the year before college. His parents wanted him to go and like go to like a major university from what I remember, because I'm always hearing it secondhand. I'm not him or his parents, but from what I was hearing was his parents were like, you need to go to college. And he's like, no, I'm going to do this company thing. And he's like, his parents are like, well, how much are you making? He's like 25, 30,000. They're like, damn, that's a good bit of money. But come on, you know, if you're going to have a family, support a family, you need to go to college, all these things. Well, the company turned out really well, and I think he sold it. And he's done a lot of cool things like Rico Brooklyn, which took storm damaged trees and turned them into all this stuff. He's using the API and all these different things, like working on their API. He works at Moon Farm, right? JavaScript. There's the TypeScript, Angular, JavaScript, Node, React. Does he know that he is a BAS? He is for us. I think he does a good bit of coding and stuff. But yeah, and then Nanika connected to him. Nanika is one of our Hasm scholars. Can imagine Ron coming while in college. Exactly. And I'd love to have him come in and talk about these things. Really great guy. Here, I'll show you one last thing on Dan Richfield. But he's an outlier. So we're going over to his uploads now. Little did he know when he was uploading these videos that here he is. He's built earth farms. There's Dan right there. So he builds these earth farms right here. Earth ships. Yep. Nanika's awesome. Here he's with the dude talking about the whole process. He has an apartment. He had an apartment in New York City. But Dan is such a cool, interesting guy. Does a bunch of bouldering. I don't know if he's still into bouldering and all this stuff, but yeah, so we'll have to bring Dan on and have him come in and talk. That, man, that's just that grip strength right there and stuff. That'd be a lot of fun. So we'll have Dan come on. We'll talk about that stuff. But Dan is definitely a what? Which I wish we would all be this. What is Dan? Theme of the day. Dan is definitely a what when it comes down to it. Dan is an outlier. He's an outlier because you wouldn't think, and nothing wrong with it. Like you wouldn't think, oh, you are highly proficient in coding. And so how do you think Dan got good at coding? He doesn't have a bunch of college education to learn how to code. He doesn't have a Brian Stevens. He has his own motivation. He has his own, I'm going to learn how to code. I'm going to do these things. I have to know this. I'm going to go find this. Stack Overflow. Hey, man, Stack Overflow is one of the best things out there in the world. So we're going to go and we're going to try to be more like these outliers. But maybe not like these outliers. So practice makes perfect right there. You got it. So these points right here, which of these are the biggest outliers? Which of these points right here are the biggest outliers for the model? I just drew in the model so you can see it. Which of these points are the biggest outliers? Which of these points are the biggest outliers? Red is a huge outlier. And how can we kind of talk about things that don't follow the trend? Red is probably the biggest outlier. Great job right there, 50 points. Excellent work right there. Green and red, I'd also agree green pretty much too. What's a good way to measure an outlier? What's a good way to like talk about mathematically what an outlier is? Like how mathematically we could calculate this. I mean, we've got here the actual, we've got here the predicted, and then mathematically we could get the this. And what is that? What is E? E is the residual. Max, great job, just crushing it, man. We've got here residual. Now it can be used for the it can be used for the residual standard error. The residual standard error is a typical miss. It visually, and I think this might help to see it. If you think about what the RSE is, it's usually about a half width of how far your residuals are out. It's usually something like this. It's a plus or minus for like how far out. Does that make sense what the RSE is? It's about how far out the residuals are. So it's not how far out they are, because some people say our model will miss by this. We don't like that will word here. Sorry, any wills in the chat. But it's about how typical the residual is. So the residuals are typically maybe for this model about this distance. There are some extremes, though. There are some outliers. But the RSE is about the average distance a residual is away on a plus or minus scale. So the RSE is the typical miss we make, but each miss could be calculated by a residual. So with this, we need to know that the effects that these things have are going to be based on two quantities. Now, I like to go out and invite my my little nephew Tolliver out for these examples. So Tolliver, let's call Tolliver out here. Tolliver's getting bigger by the day. He used to be really, really tiny. So one of these days I'm going to start inviting Everett out to these examples. There's Tolliver. And here's Uncle Brian. And we're going to go out. Let me move us around so I can move us. There we go. There's Uncle Brian. There's Tolliver. Tolliver, you go up there. So now we're going to go out right here. And we're going out. You ever see one of these things right here? Where are we going out to? Where's Tolliver and Uncle Brian going out to? He's off the screen. Where are Tolliver and Uncle Brian going out to right now? We're going out to what? Here we go. I'm going out to what right here? Little seesaw right here. Now, Uncle Brian is going to take and jump down on the seesaw right here. Decrease size of Uncle Brian. So I'm going to jump down on the seesaw right here. What's Tolliver going to do when Uncle Brian jumps down on the seesaw right here? You could put Tolliver on the other side. You got Tolliver go over here. Okay. What's going to happen? Oh, he's going to get launched? Really? Really? Oh, wow. What happens when Uncle Brian jumps down on the seesaw right here? Right there. Right there. Right there. Look at where I'm jumping on the seesaw. Nothing at all. Nothing at all. Why? Explain to me with terms you may know. I'd love it. Rip my knees. 100 points right there. So before he was in the middle of max. Sorry, I changed him, right? Brian does not have any what right now. Use a term you know, which you'll be hearing again very soon. Brian does not have any what right now. Brian does not have any what right now. I jump down from this height all the way. I go, whee, right there. Leverage. It's almost like it's going to be used again. So I jump down from up here and I land right here. But let's say I go over here and I just lightly go from right here. If I go just lightly, what's going to happen to Tolliver right now if I just lightly? Uncle Brian just lightly, kind of, you know, when you got your knees, you're with a little kid or something, you got your knees just lightly. So what's going to happen right there if I do that? Just lightly. Broke the seesaw. Sorry, Tolliver. Just lightly do this. Just lightly. I'm going from like this height right here. Anything? Probably not that much, right? It's gonna move it. Does that make sense? Not that much. It'll work much better. It's not gonna be too impactful on the seesaw, right? But now Brian says, aha, I'm gonna go up here off the screen. I'm gonna jump down. What's gonna happen now? Do you see what's gonna happen now when I jump down from up here? I jump down from up here, and when I land on that seesaw, he'll do the animation. And then all of a sudden, wah! There you go. Sorry, Tolliver. Tolliver's being sent to the moon. Like Dogecoin. I can't even speak. So what are we talking about? What is this? What are you doing, Brian? Do you see it? What we're talking about is the same sort of things right here. When I was talking about Brian landing on the middle of the seesaw, I was talking more like a point like the what right here. Brian landing on the middle of the seesaw might be more like the what point in this model. Brian landing on the middle of the seesaw might be more like the what point in this model. Tolliver will be the new GameStop eventually. Brian landing on the middle of the seesaw might be more like the what point for this model. Not the blue, on the middle of the seesaw. The middle of the seesaw might be more like the what point. The middle of the seesaw might be more like the green point. That's the middle. That's towards the middle of the seesaw, right? Now, when Brian, remember the second example where Brian was just lightly on the seesaw? Brian lightly on the seesaw might be more like the what point. Brian lightly on the seesaw might be more like the what point. Now Brian just kind of lightly on the seesaw, not going too extreme, not jumping on it, might be more like the what point. Brian just lightly on the seesaw might be more like the what point. Brian lightly on the seesaw might be more like the what point, or I'm lightly on it, the blue point. That's Brian lightly on the seesaw. But last but not least, Brian jumping on the seesaw and impacting it majorly is actually the what point. Now it's in a reverse, it's reversed here, but Brian jumping on the seesaw or massively impacting the seesaw with a lot of leverage and far away from it is which one? Where we have a lot of leverage and we're far away from it, the red point. So it's almost like we need two components to be what on a model? We need leverage, which you see right here, which is your X space difference. And you also need what is called deleted studentized. And what do you think the R stands for right there? We also need a deleted, we'll talk about what that means in a moment, but what do you think the R stands for of deleted studentized and whatever the R is? Like fill in what the R would be, because you already know a term for this, but we're going to use another way. Residual right there, deleted studentized, and we'll talk about what the deleted studentized portion of it means. But if you notice here, it's two components, and this is the Y component. So the Y component over here is going to be how far you are away from the model, basically, which is a term for an outlier. So you can see right here, why is this right here really not impacting this model? Why in example 2, explain to me briefly, why, and think about this, here's our seesaw, and there's where the center of the seesaw is at. So why is this point not that influential on the model? Try to use your words right here, or studio. Oh my gosh, David, I'm throwing 100 points. Or not that it has no deleted studentized residual, but Nathan has added some extra. Nathan getting those points too. It has a smaller deleted studentized residual. So it has a much smaller deleted, and we'll talk about what that means. You can just think of it as a residual for a moment because they're going to be similar. This point is influential because according to the original line, it has a large residual, and then it has large leverage. If that's where the center of the x's are at, it has both components right there. It needs both components to be what? Say it with me again. To be this, you need both components. If you have 0 for one of them, you are not this. To be this, you need both components. And we'll talk about those components. They're listed on the screen right here, right here. There's the other component. To be this, you need, and let's get 100 points. I want at least 5 people to say this. To be influential, 5 people. We need 5 people right now before those points. I'll wait. I know we can do it. To be influential, you need both those components right there. Both components. Thank you, Clay and Julia and Veda. To be influential right now, so make sure to put influential in the chat. You need both those components. Well, where's everyone else saying it? Good faith points right there. Got almost enough. So outliers, great job, Money Max and Clay right there. So outliers can hide in histograms and scatter plots. The reason being is because if we look at something like this right here, is Brian unusual if he weighs 140 pounds? Great job, Wilton, right there. Is Brian unusual if he weighs 140 pounds? Which I'm just giving you one characteristic, like Brian weighs 140, which would be histogram. Here's a histogram of weights of students. Is Brian unusual if he weighs 140 pounds, which might be somewhere towards here? It might depend on other factors. Is Brian unusual if he weighs 140 pounds? Well, 140 pounds, if someone says my friend weighs 140, you'd be like, that's not that unusual. But what if I tell you Brian is 6'3"? At that point, you might be like, well, that's pretty light for 6'3". I think my brother weighed like 135 in high school and he was 6'3". You'd be like, well, that's really light. I mean, no judging. But when we say unusual, we mean not towards the central tendency of the data. So unusual doesn't mean bad. Outliers are unusual. Once again, Dan's not bad. It's just that he's unusual. So Brian might not be unusual in terms of where he is. If I don't weigh 145, but if I were to weigh 140 or 145, then it's 6'3". So when we do this, we might have to look at scatter plots, but scatter plots only analyze how many variables? Histograms analyze this many variables. Scatter plots analyze this many variables. How many variables does a scatter plot analyze? How many variables does a scatter plot analyze? Histograms only do 1. Scatter plots analyze 2. But what if someone's unusual in like 3 ways? Like the combination of their x's, like multivariate way is unusual. Like it's unusual to have this height with this weight and this body mass and this other thing. That's an unusual combination. So they could still hide from us with these sorts of graphical techniques. So when we try to figure out how unusual something is, we need a holistic way of looking at it. And the way to look at something's unusual nature from how far it is away, because it's really easy to see in the one variable sense. You just go right here, you put everyone on this, and you have everyone stand here. And we call it what to see how unusual people are. There's everybody chilling out. So what do we call it to see how unusual people are from each other? We call it what to see how unusual people are. To see how unusual people are, the terminology for the unusualness is your leverage. And we can calculate this. So it might be hard to visualize, but the mean of the x's is going to give us, we can calculate someone's distance from the mean of the x's. That's what I'm trying to say. So it's multiple x's right here. It's not just one x's, but it's multiple x's. How far are you away from the mean, x bar, of the x's? So we'll calculate. So leverage only accounts for the what variable. Just make sure it's clear. Leverage is only how far you are away on your what characteristics. Leverage is only your what characteristic. Leverage is only kind of, it's how far are you away from the mean of the x's. It's not quite like spread. Spread is associated with leverage. So the more spread a variable has, the higher leverage it could have. Like that variable would bring more leverage to the model. Like things that are farther out on it would have more leverage depending on combinations of their x's. And it's a multivariate sense. It gets a little complex, doesn't it? Because now we're just looking at 1x, which is easier. So this is just like 1x, like the seesaw example. It's the easiest way to understand with just 1x. And then in the multivariate sense, so this is the one variable sense again. So you can see here high leverage points, extreme values. And then we go to the multivariate sense. Now, what do you notice about this plot? And you have to notice this about leverage. Leverage only deals with the what? Is there some sort of statistical anyway? Kind of. I mean, that's regression pretty much. Regression is about the mean of y at certain values of x. So we don't really do the mean of x. We predict the mean of y at certain values of x because that's what our line does. And what do you notice about this plot right here? Because it's not a regression. This is not a regression plot. You're like, wait, that's regression, right? Let's just fit a line through that. That's not regression. This is not regression. This is looking at the leverage. And this point right here has the highest leverage. And this point right here would have the lowest leverage because this point right here is the what of both whats. That point right there is the what of both whats. Well, not too wise. These are both x's, right? So that point that I've circled right there is at the what of the whats. So it's like it's like a guy who's 5'11", 165, 3.7 GPA. It's at the mean of both variables. So that individual right there has the least leverage because they're going to be where on this seesaw. Do you see where that person would be on this seesaw right here? Like if they got off the seesaw, nothing's going to happen. What person is that on the seesaw who's at the mean of the x's? If they get off the seesaw, nothing really happens to it. They hop off the seesaw, and the seesaw really doesn't move because they're standing. Nathan, you kill me, man. I love it. That guy right there is at the middle of the seesaw right there. And just if they get off, it's not really going to move. The seesaw is already balanced the way it is. And they're just standing directly on the middle of the seesaw, and they have no leverage on it. They could just start jumping up and down, and nothing's going to happen. That individual right here is at the mean of the x's. Make sure you understand that leverage deals only with x's, and it's how far you are away from the mean of the x's. The individual over here has most leverage. Why does that individual right there have the most leverage? When we want the 2x variables, yeah. So actually, this right here could also go to, because and you're talking about multicollinearity, you are correct. So you wouldn't want your x's to have a relationship, and you could look at this does look to have some sort of relationship right here, but then this is only looking at the leverage component of the x's. No, Max, you are 100% correct. Max, 50 points right there. You are right, Max. You don't want them to have relationships like this. So it could still make a scatter plot far from each mean of each x. Exactly. And we could think of it as a residual. Well, so here's the thing too. This point, and don't think of a model for this. Don't think of a model. Or that we could do the other point. This point right here, which we have circled here, follows if we were to put a model through this, the model. But does this point have high leverage? Does this point have high leverage, yes or no? Does this point right here have high leverage, yes or no? And explain to me why that point right there has high leverage, yes or no. Does that point right there have high leverage, yes or no? Yes, and why? Does that point have high leverage, yes or no, and why? It does have high leverage. Why? This is not a y, this is an x and x relationship. This is the mean of the x's. And guess what confuses people? It's far from the mean of the x's. It's far from the mean of the x's. This can get very complex, and I don't want to really bring it to this, but if you've ever heard of eigenvalues and eigenvectors, if you do the mathematics on this, if we break it down to an eigenspace, I'm literally not going to do eigenvectors in eigenspace right now, but the eigenvector on this is much shorter, and the eigenvector on this is much longer. So this is more unusual in terms of the eigenspace. Don't worry about eigenspace. We're not putting that kind of stuff on the test. But think of a density cloud going out. The density cloud would have to go further to get this one. This one's way more unusual because it's further out on like a density cloud. I'm not going to do eigenvectors in eigenspace though. Even I get a little bit iffy on that mathematics because there's some upper level mathematics that goes into this stuff, but we don't do that in business analytics. So notice here, which of these points is the most influential? Point 1, and it's easy to see if you look at the graphic. Point 1, point 2, or point 3 is the most influential. Point 1, point 2, or point 3 is the most influential on that sort of data collection. And we're talking about the red point here. Point 1, point 2, or point 3 is the most influential. Point 1, point 2, or point 3. And just think about what influence does. Careful. Point 2. What does it mean for something to be influential? Influential means it's going to do what to the line when we add it. If something is influential, it should do what to the line when we add it. If something is influential, it should do what to the line when we add it. Don't worry, 50 points, David. I appreciate David jumping out there and answering first. I like that. So if something is influential, it'll change. It's going to influence the line. That's what influential. This one has the most leverage. Great job, David, right there. David, recovery, 50 points. You got it. David's pointing out that this one has the most leverage, but you need another component. So you see that one has the most leverage. You are correct, David. That is one of the highest leverage points. This one has no leverage. So what is that other component Brian said you need? The other component I said you need to be influential is a what? Put it in as an acronym, 3 letters. So, and we'll talk about how we find this here in a second. The deleted studentized residual. So I want you to do the following. If I were to remove this point right here, how would the line look if I deleted that point? If I deleted that point right there, how would the line look? If we take this line, we take this point and delete it, then the line would look what? It'd look flat. So what will we do now? We will take and delete the point, and then we will calculate the residual from a line where it doesn't have influence. This is a residual, but why are we calling it a deleted residual? And then that's the next one we're going to talk about, studentized, Kevin. Why do we call it a deleted? Why do we call it deleted? Because we do what to get the line? What do we do to calculate the line that we're going to calculate how far it is away from? To calculate that black line right there, we delete the point and we calculate a line without its influence. So this is going to be a line calculated without it. So the deleted portion here means delete the point and calculate its residual. But studentized is the weird word. And studentized might as well mean standardized. So when we talk about studentized, we're actually talking about a t-statistic. And just think of it as a standardized metric. So when would this be extreme? And here's a hint. When would this be extreme if we're doing t-statistics? Outside of what and what would it be extreme if we're doing t-statistics? Because studentized just basically means standardized, but it's studentized because it's the t distribution, not the z. If it was standardized, it would be a z, but we call it studentized. And just think of it as standardized. If you called it deleted standardized residual, I probably wouldn't care. A statistician would freak out, though. This is not on the midterm. This is not, I'm going to triple check, but this is not on the midterm. We will be doing a review next week. So we're going to say, how likely is it that? Oh, the midterm is next week. 100% midterm next week. This shouldn't be on the midterm, though. I'm going to double check. I will send out more announcements, and we will be doing a review this weekend. We'll be doing Kahoot this weekend. Lots of announcements to come. Brian getting caught up on everything. So the deleted studentized residual is the absolute difference between that point and the recursion line at that point. Correct. That is correct right there. The deleted studentized residual, not the absolute difference. It can be negative. It's just a residual. So here's the definition, Max. A deleted studentized residual is a standardized metric, we're going to turn into a t-statistic, of a residual calculated without the point's influence on the line. So it's just a residual without the point's influence that's been standardized to a t-statistic. So we find the difference in the line of yes. That's what the residual is. And it's deleted because we're removing the point out, so the point doesn't get to influence the line. And then what would be an extreme t-statistic? An extreme t-statistic, which would be an extreme standardized value for it. What would be an extreme standardized value? If we had an extreme standardized value, studentized value, an extreme studentized value would be outside of this metric. So think of t-statistics and how they work, and what would you expect 95% of the time? What would you expect 95% of the time a t-statistic to be between what and what? 95% of the time I would expect a t-statistic to be between what and what? 68, 95. And this is, remember, the studentized portion of it, so it's a t-statistic now. So that way we don't have to look at like it's 100. Be like, oh, well, it's 3.8. Ooh, 3.8? 2. Exactly, Max. Since it's studentized, great job, Max, right there. Since it's studentized, we're just using the curve for it. 68, 95, 99.7. So a t-statistic outside of 2 or negative 2 is very unusual. Don't worry about calculating leverage right here. I'm not a huge fan. You could put this on your formula sheet. I highly doubt we'd put it on the final, but this is when something has extreme leverage. Something has extreme leverage on model dependent. K is the number of variables and N is the sample size. So that is calculated for you, and we'll see it here in a second. Something has a large deleted studentized residual when it's more extreme in absolute value than what? And this is a review of what we've been talking about. Something has a large deleted studentized residual when it's more extreme in absolute value than what? Something has a very large, extreme, unlikely by random chance, deleted studentized residual when it has a deleted studentized residual outside absolute value of what? Which it doesn't say that in the notes, but we can deduce it. Larger in absolute value than what? Because it doesn't matter if it's positive or negative.
It doesn't matter.
That just tells us if it's above or below the line. Deleted studentized residual being very large would be more extreme in absolute value than what? 2. Max, excellent work, Max. I'm just going to keep throwing you those points, man. You got this. And David, great job. You got to be here. You got to practice these things. You got to say it 10 times. You got to make sure you know that 2, because the 68, 95. You know what's, Max, is so interesting? Does this sound like p-values again? Because what is the area outside of this? What is the chance of a deleted studentized residual being more extreme than 2 or negative 2? What is the probability that a deleted studentized residual will be more extreme than 2 and negative 2 by random chance? By random chance, the probability that a deleted studentized residual will be more extreme is basically, and we're doing a p-value, right? And the probability of a deleted studentized residual being more extreme than 2 or negative 2 by random chance is 5%. We're back to the start of the lecture again. These topics coincide. There's a lot of, why are we using 2? Why are we using negative 2? Because you would expect most deleted studentized residuals to be very close to what? And we'll see a graphic here in a half second. This is the influence plot. This is how to check this right here. So all we're doing is checking it. All we're doing is checking it. So is there a p-value? I guess you could kind of do it. We don't really do a p-value. We get the following plot. So here is leverage. This right here, and I always forget the equation, so I don't want you to memorize either. 2k plus 1 over n. I had to memorize it when I was in school. No, I forgot it. So 2k plus 1 over n. This right here, anything beyond this point has what? Anything beyond this point, explain to me. Anything beyond here has what? Anything beyond that line has what? Anything beyond that point has what? So that is the formula to figure out where this is at. And this is the measure we're looking at. And these are the x's. That's actually the mean of the x's down here at the bottom when something has no leverage. So anything beyond that line I drew has what now? Anything beyond that line I drew has what? Basically, Kevin's some 50 points right there. Yes, but go a little more detail. Everything has leverage unless it's at the mean of the x's. Everything has leverage unless it's at the mean of the x's. Everything has leverage unless it's at the mean of the x's. Because you notice like this has a leverage of like 0.08, this has a leverage of 0.06, this has a leverage of 14 about or 13, this has a leverage of 16. So everything has leverage, but points beyond this line have what? It's not quite an outlier. Because this won't have anything to do with outliers. Remember, leverage is just going to, it has high leverage, and leverage is just how what you are. Leverage, which this is not an outlier, remember. So large leverage, Justin, great job right there. And don't worry if you get things wrong, just keep answering questions. Outlier will be considered by the deleted studentized residual. Leverage is just how far you are away from the mean of the x's. Does that make sense? So anything beyond that line right there has high leverage, which means it's far away from the mean of the x's. So it's like finding this point, well, it's in the previous graphic. It's like finding this point right here, which has very high leverage. And so that point right there that has high leverage would be somewhere over here. So that is the highest leverage point. It's furthest away from the mean of the x's. Does that make sense? So that is the furthest away from the mean of the x's. Where are these lines at? Where are those lines at? These lines are exactly at what number? You can do the absolute value. It'll pull the model more. Think of the seesaw example, Cole. So like the mean of the x's is like the center of the seesaw. And the further you are away on the x's, the more you impact the model. So points far away from the mean of the x's will pull the model towards them more. But now we need to look at the second characteristic. Does that make sense, Cole? So if something has high leverage, it can be influential. But why is this point right here that I've circled not influential on the model? Why is that point right there not influential? It has very high leverage. Why is that point right there not influential? Why is that point that I've circled, it's very far away from the mean of the x's. Why is that point right there not influential? That point right there is not influential because the deleted studentized residual absolute value of the max, crushing, man. It does not have a deleted studentized residual outside absolute value of 2. Its deleted studentized residual is within -2 or 2. So you must have two components. You must be unusual in your y, and you must be unusual in your x. So you must be far away from the model. Think about this. This point right here is like our previous points, like this one, which this does not have a deleted studentized residual, but it has leverage. So let's look at points where things are influential. Aha. This reports to the row number of the thing that is influential. Person or row 39 is very influential in this model. But there's a point with more extreme leverage. Do you see it? It's right here. But this would be where? Almost perfectly where? Something with a deleted studentized residual of 0 would be very close to the what? So this has extreme leverage, and here I'll draw it out for you. If we were to look at this model, the model might look something like this right here. And that point might look something like that. It's going to be on the line. It's like almost perfectly on line. Now, this is a deleted studentized residual, but the deleted studentized residual is very close to 0. So the line, when we calculate this residual with the line removed, just a little bit further down. Oh, yeah. Oh, great catch right there. It's going to be a tiny bit. He's going to be right below the line right there. Just a little bit below. What David said. Nice job, David. And so understanding what this is showing you is very important. This is the point at which things have what? Any point beyond here, we would say has high what? Any point beyond here has what? Any point beyond this line, this is the, I don't want to write the equation. I never remember that equation. I just don't do it. It calculates it for you. It finds it for you. You just have to know that line right there tells you when things have high this. Beyond this point right here, anything beyond this has high leverage. High leverage, because we're on the x-axis. And then anything outside of these lines right here has a large deleted studentized residual. So this point right here, which is this row, is something that is what on the model? One word. That point right there has undo this, like too much this. And that's actually what the size of the circles are. The size of the circle is the size of the this. And it's like the importance in the model and how much it's impacting the model. And that's got a lot of impact on our model. So that point right there has too much what on our model. That point right there has too much, that singular point we're saying, that point really has too much this on our model. We don't like it because it's really controlling what we're doing. The model's like pushing it towards that point right there. It's going to overly do it. It's going to have too much influence. And it's a combination of its leverage and deleted studentized residual that's giving it influence. You notice right here, there are actually some points that are not found. These points over here have a lot of influence, but just by the metrics we use, they're not found. But look at this model. That's all these points that fall into these regions right here. Way too much influence. You'd say to me, Brian, there's a lot of influential points in this model. Interestingly enough, these points over here do not turn out to be high influence. They did not have a large enough deleted studentized residual. They're very extreme in their X values, though. So when we do this, we can take a look at the points we're interested in, and we don't want to just throw these out unless, and let's go look at one of our models, unless we think the person's lying. We've got our height weight data set right here, and let's go run an influence plot on this. Here's the influence plot of the individuals who have undue influence on our model. Let's go take this as a vector right here, and this is what you're seeing in the slides, and go to survey 10, and go to these rows and read about these people. Here we go, are the people, and we're just going to the row space and finding out about these people. Undefined rows, columns, what did I do? Why didn't it work? Oh, columns, haha. I'm smart. There we go. Let's look at these people right here. We're only looking at heights and weights. So I think we only need to go like 1 through 5. They should be contained in the first 5. Okay. Tell me about this person right here. This person right here, tell me about them. That person right there, tell me about them. I don't know if they exist. They want to weigh 250 pounds. But I think they're this person. I could calculate the model without them. I go to minus row 544 and recalculate. So they are, oh no, they're this person. You see how they go away? They're this person right here. That's who they are. Because I removed them. That's 544? Yeah, that's them. So they're, if you notice, when I recalculate, they go away. They are a big outlier. But they're this person. They're far away from the model. They've got pretty good leverage. Exactly. I agree with Daniel right there. They say that they're 75 pounds. Maybe they meant 175, or maybe they double entered in their height. They're saying they're 75 inches tall, and so I totally think you can remove that person. We don't just remove people from the model, but I would literally almost have to lose 100 pounds right now. I guess I'm in need of weight loss to be this person. So if Brian loses 100 pounds, he might be with that person right there at their 75 pounds. Nothing wrong with whatever weight you are. Personal opinions with Brian. If you're as tall as Brian, I don't think you should weigh 75 pounds. Just putting that out there. Don't think so. So we can use this. We can sometimes remove things. It just depends. We don't just remove things we don't like. Why was Brian able to remove that? Because that just shouldn't exist. You can't do that. You don't just remove things. I probably wouldn't remove those other ones because you can be like 5'3" and 270. You can be all those other weights. Extrapolation, probably one of the easiest topics to talk about. We went from a pretty in-depth topic, pretty like theory questions you probably haven't heard before, to now we're talking about extrapolation. What variables does extrapolation occur on? What variables does extrapolation occur on? What variables does extrapolation occur on for 50 points in the chat? What variable does extrapolation occur on? Extrapolation, the X variables. When you hear extrapolation, not extrapolation, but extrapolation is on the X variables right here. Great job, Emily and Veda. Excellent work. Extrapolation. So when we do this right here, extrapolation is going to be how our model works on data that is outside the X's in the model. Now, here's the issue. In simple regression, it's really easy to see if something's outside the X's. Like, let's look at our model. You ready? when would this model be extrapolating? Explain to me briefly when this model would be extrapolating right here. Pretty easy to see. Be very careful. A lot of people usually forget. When is Brian's model for 50 point extrapolating? When would I extrapolate using this model? This model would have to extrapolate to make predictions where and where. There's 2 spots. Remember, extrapolation is outside the X space of the model. So look at the X space of the model and then tell me, when are you outside of the X space of the model? Max, you are correct. I mean, that is correct, Max. Well, nice job, Max. I'm throwing more points out there. Yeah, and so around a weight of 300 or around a weight of 100, Max is very correct. Great job, and David too. Generally below 100 is where extrapolation starts. I think 75 might be the min. You could go right here and do a summary. Probably the quickest way to find out where extrapolation begins is to go to your X variable and find out 75 and 305 are the values right there. Around 100 and around 300, yeah, and Max is correct. Max did put some values by which we would have to extrapolate to make predictions. His 13,413 is a big extrapolation of the model. That's crazy. So when our model has to make predictions outside the X's, what is going to increase? We're going to have even more what? Now, I want you to change this word to another word because we'll have more of this when we make predictions that are extrapolations from our model. The this is going to increase as we extrapolate from our models. The model kind of accounts for this, but it's even a bad idea. Uncertainty, Wilton knows what's up right there. That's uncertainty. So we'll have more uncertainty as our model predicts further out. We can choose to make predictions for individuals, which would be prediction intervals, or we can choose to make, for 1x, or we can make for combinations of x's for multiple regression models right here with extrapolating. So let's take a look at some of this right here. And once again, we're looking to see if the combinations of x is odd, which is really hard to see. So right here, the model is going to have a harder time predicting who. So this is once again our x's. So notice how these are just x's. I'm going to circle it instead. So our model is going to have the hardest time. It's pretty obvious. Our model is going to have the hardest time predicting who because they're the most unusual in their x's and they're the furthest out from the center of the x's, which is really just a measure of leverage right now. So the person who is the star is the most unusual, and thus the model is almost extrapolating to predict them. So the model is going to have the most uncertainty when it tries to predict this person because they're not like everybody else. The more unusual you are, the more the model has to work to predict you. Just think about this. The model learns really well on these people, and then when it gets to this person, it's like, well, you don't follow the trend, so I don't know how to predict you very well, so I have more uncertainty. So we can use the code right here, extrapolation check, to see if something would be extrapolated. And all it's going to do is tell us what percent outside this density cloud a point is. So as we build this density cloud, where do you notice this last point is at? It would be in the what percentile. It doesn't have right. I see what you're saying. You have to do the density cloud. I see what you're saying. So Max, great question. By distance, this is such a good question. It goes to upper level math. By distance alone, this point is the same distance as, or might even be closer than this. But in terms of eigenvectors, we won't get into this, don't worry, which this is done for you. In terms of eigenvectors, which is kind of a principal components breakdown of the space, that point right here has a larger eigenvector or is more extreme in the eigenspace. Don't worry about eigenspace. I should probably stop saying it. It's a, yeah, does that make sense? In terms of like distance, it might be the same distance or even closer. But in terms of like, if you think about the variation on one, I'm trying to say it, what is it? Orthogonal space, 90-degree space versus the variation on another 90-degree space. Did you notice how there's less variation here, but it's way further away? There's more variation across this. Yeah, the clouds, I think the clouds help me see it. When you look at the clouds, like a cloud going out, the cloud would go out by the density of the data. So as you think of like a shock wave, the shock wave is going to hit this last. So that's the furthest out in terms of you can think of that, how the space of this data exists as a shock wave. And that point right there is the most extreme out. I think these visualizations help because we're not ever going to solve for eigenvectors or eigenspace. But that sometimes someone who's a math major, like they're like, oh, of course, yeah, I could solve you the eigenspace. I'm like, I don't want to do that. So the code makes it really easy though, because what does this represent? This value right here represents 100 being that this point right here at the 100th percentile is the what-if away from the mean of x. If it's at the 100th percentile, that point is the what-if away from the mean of x. Here's the mean of x, which this would have a 0%. If we plotted this one, it would be at a 0 percentile. That point being at the 100th percentile right here is the what-if away from x. If it's at the 100th percentile, that means it's the what is point away from x that we checked. Considering all the points in the model and the point that we're checking right there, that point is now the what is away from the mean of x. If it's at the 100th percentile, think about that means the percent of points you have to go through to get to it from the mean of x as you go this shockwave out. You have to go through 100% of the points. So in terms of the space, that point right there would require the most extrapolation. It's the furthest away. Great job, Wilton, right there. That point right there is the furthest away. How about point number one? Point number one is over here at 45, meaning it's at the 45th percentile. So that's not too far out. You don't have to go through too much of the data. And this one right here is at the 93rd percentile. Do you want these numbers to be high? No. That means these points right here mean how far you are away from the center of the x's, and the further you are out, the more what is required and the more this there is. The further you are out, the more extrapolation you're doing and the more uncertainty there is. So if you are further away from the mean of the x's, like this point down here, you're going to have to do more extrapolation to figure out the point and its estimates and its uncertainties, and you will have more uncertainty for it. So we don't love this. We don't want this. Let's mention this briefly right here to finish class because it's kind of a cool thing, but we'll come back and revisit it, and we'll do polynomials and interactions next class. So variable creation is one of the coolest things ever. Who went to the Business Analytics Society last night? Who went to it? Anyone? I think Veda. Was Veda? I've heard through the grapevine. I'm trying to think who all was there, but people were like, oh, I saw so-and-so there and so-and-so, and I just can't wait to see everyone. David was there. Veda was there. Max was there. It's awesome. I don't know. It really meant, it was so weird because usually I get the interactions. So when I was doing the presentation, I was like, I couldn't see anyone. So I was like, I don't know if people were responding, but people were probably like, I don't want to talk. It's late at night. I just want to eat some pizza. But luckily there got some laughs in the room, especially with my Word documents. I have closed down Word since then. I've only got about 20 documents open from today. So variable creation right here. I'm going to just mention this briefly and we'll come back and talk about it. What we have right here is a Kaggle competition. This is why I mentioned the Business Analytics Society. We were talking about last night the Big Data Bowl for a moment. And it'd be really great if we get some teams going and people participating in it. And it's just to learn and just to maybe win some prizes. Probably not win prizes, I'll be honest with you. Probably not win prizes, but definitely learn. Here's a model predicting the log 10. We've transformed the y variable using what x's. What x's is somebody using right here? Y tilde dot. So they've done a transformed y. They've said, let's take the log 10 of y because y maybe has a skewed shape right here. Yeah, I know. That was, yeah. It's the unintentional jokes that work so well. Like, I heard the room crack up, and that's the best reaction. Thank you, Max, right there. All the x's right there. All the x's. So this is all the x's. So you would say to me, well, if you only get an r squared of this, I mean, what could you do? This is pretty good. It's got a good r squared adjusted. The model is statistically significant. The typical miss we make is 0.5. You round it. So overall, this model is pretty good. Just make sure you understand this output. Once again, this is a bit of a review. We're going to do this next class too. But predicting the log 10 of sold at week 26 using all the x's, we typically miss by about 0.5 when we make our predictions. We explain 62% of the variation in the log 10 of sold week. The r squared adjusted tells us that we probably haven't added too much to our model because these two metrics are pretty close. This is the penalized r squared. F statistic, we're not going to worry so much about. It's 300, which says we explain 300 times more variation than we would have expected via random chance. And the p-value for the model is super significant. But what if I told you, and here's the oof. Oh gosh, I got to ask. Do you see any problems with this model? Maybe like some linearity, some normality of residuals. P-values for these are going to be 0. What if I told you someone won $5,000 creating their own variable, and look at this R squared. The R squared here is 98% basically, and the typical miss is about 4 times smaller, maybe even almost 5 times smaller. So now their typical miss is 5 times smaller, 1 minute warning on the class. And what they did was they created a variable of the log 10 of sales in week 13 over the stores in week 13 times the stores in week 26 to predict the sales in week 26, the log 10 of sales in week 26, like a understanding of what were we selling in week 13 based on the stores. And then if we know how many stores are in week 26, maybe we could predict the sales in week 26. Like this understanding got them $5,000. And look at your model. What main fix, last question, 100 points, what main fix between this model and this model do you see fixed, which is a key assumption for the things we do when we do this sort of regression? Now, one of these is pretty bad over here. This is a probably major concern, but what key fix do you see that I'm like, yeah, it's not so bad on that anymore. I know it fails it. I know the p-value fails. But which one do you see? Just seconds to go here. Let's do 500 points in class. What key fix do you see? Veda crushed it right there. Great job. 500 points. Linearity looks to be way better, which is a key assumption for linear regression if we're going to fit that line. And that's got it. Residual plot for linearity looks way better. The normality is... Remember we started class talking about that model that did 98%? Well, here's another model that does 98%. It's definitely the wrong model, but because the normality of residuals are pretty darn bad. But I would say... I know we're done. I would say this model is wrong, but it probably is very what? Considering it once won $5,000, because this is wrong. That's bad. This is okay over here. The equal spread's okay. Linearity's probably okay. Both those are okay. I would say this model is wrong, but it's probably, considering that it does 98% of the variation, it's wrong, but it's probably very this. Useful. Veda another 100 points. Great job, everybody. That's what we're here to do. We're here to practice, and I really like how everything goes full circle. If you can't tell, a lot of these topics coincide. We're doing the same things in 474. You saw the 474 slides earlier. Literally, that's not 474 slides. You saw it earlier. We were talking about literally the same ideas with an R squared for this model right here of 98%. Full circle. R squared of 98%. Model is wrong, but very useful. Back to our class. Really? R squared of 98%. Model is wrong, but useful. Happens all the time. You get a wrong... All your models are wrong. But your model can be very, very useful. And that is just how we do. We'll talk more about variable creation and then polynomials. Man, I love some polynomial models. It's just the most beautiful plots ever. We'll be having office hours here in a little bit in 18 minutes. Great job, Veda, everyone. Wilton's getting close to the 50,000 points, 50,000 point threshold. Love seeing those hours. Great job. People here practicing. Got polynomial models, interaction. Oof, interaction is going to be fun. Interactions is the one that people usually forget. We were reviewing that today in class, and people need a review in 474. Like, literally, I'm not joking. The things you are learning right now, we review again in 474. What do you notice right here? This is 474 notes. RMSE. This is the typical miss the model makes. Look at this right here. We've got interpretations, which we will be doing. We were doing interpretations today. This is 474 notes from 320. Transforming your Y and transforming your X. It's kind of like we've been doing that, right? We just did that in one of our models. Why do we transform from normality? Pros and cons of linear regression. And then the last thing I wanted to show was the interaction. Yeah, because we did interactions today. So literally today in class was probably like a 3-class review of there's interactions. And I'm pretty sure this is a slide from 320. And we'll talk more about interactions next class. So here's the thing. Look at this. So there are like 3 slides on interactions right here. But for your class, you don't get 3 slides. Because this will be your first time hearing about interactions. So you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Lots of slides. So it's a lot quicker. But this is why our classes build. So if you learn about interactions now, people in class in 474 today were just like throwing out answers. They were like, the way Y is explained by X1 depends on X2, and they knew how interactions worked. So it's very important to just get the basics down, and then we will use these in your later classes. Hit over here. And that's what I love. I have people tell me like, hey, the upper level, senior level classes are not that bad because everything I'm doing, I learned in 201, 320, 474. Like I learn it and then I use it again in another class so I can use this same knowledge. So that's got it for now. We will be back here with office hours in just a little bit. I will see you then. You're welcome, Matthew. Thank you so much. Another 100 points for the chat. Bye for now, everyone. Bye.